Today we will be discussing about regular grammar. So first let's see what is a linear grammar. So linear grammar is a context-free grammar where on the right hand side you will have at the most a single non-terminal or a variable. Also epsilon productions are also allowed. So here you can see a grammar which is a linear grammar. So if you look at the productions for S, there also we can see that only a single non-terminal appears at the maximum on the right hand side. So here we have a single non-terminal, here we have a single non-terminal, here we don't have any non-terminals for these productions. So at most only a single non-terminal can appear on the right hand side in the case of a linear grammar. Now, there is a special class of linear grammar, which is called right linear grammar as well as left linear grammar. So, in the case of right linear grammar, the non-terminal on the right hand side, if it appears, it will be at the rightmost. So, generally speaking, the productions in the case of a right linear grammar will be of the form capital A giving small x capital B, or it will be of the form capital A giving x, where x is string of terminals, and as usual capital A capital B are single non-terminal or variable. Now in the case of left linear grammar, productions are of the form capital A giving capital B x, or it is of the form capital A giving x. Now what happens here is the non-terminal, if it appears on the right hand side of any production, it will appear as the leftmost. So here B is appearing as the leftmost symbol on the right hand side. Okay, so that is with right linear and left linear grammar. Now in the case of regular grammar, what you see is that the productions will either be in left linear or it will be in right linear. That is, all the productions for a given regular grammar will either be in left linear form or it will be in right linear form. So if you look at these two sets of productions, you see that this is again a regular grammar because all the productions are in right linear form. So here, if there is a non-terminal on the right hand side, it will appear as the rightmost. Here A is appearing as the rightmost symbol. Here capital S is appearing as the rightmost symbol, and here there are no non-terminals. Okay. So now if you look at this set of productions again, this is the regular grammar because all the productions are in left linear form. Here you can see that capital A, which is appearing on the right hand side, is appearing as the leftmost symbol. Here capital S is appearing as the leftmost symbol, and the other two productions again there are no non-terminals. Now here you are also given a set of productions in which are not regular grammar. So if you look at the productions, you see that as the capital S has got two productions here. In the first production, capital A is appearing as the rightmost. So it is in a format that is required for right linear grammar. But in the second production, S is appearing as the leftmost symbol. So here, what you find is that it is in a form that is required for left linear grammar. So as we have already told, either all the production should be in left linear or all the production should be in right linear form. So this is not a regular grammar. So now we will see how we can convert a left linear grammar to right linear grammar. So the algorithm that we are going to discuss assumes that the start symbol does not appear on the right hand side of any production. So if it appears, what you can do is that you can introduce a new non-terminal, say like S0, and you can add a new production like S0 giving S. So now S0 is the new non-terminal, and now S0 being a newly introduced non-terminal, it is not going to appear on the right hand side of any production. Okay. So now let's see what are the rules for converting a left linear grammar to right linear grammar. So if you so we look at productions for corresponding to start symbol, as well as productions corresponding to all other non-terminals except for the start symbol separately. Okay. So for the start symbol, if you have a production like S giving small p, where p is string of terminals. Okay. So there, what you do is you add that productions to the grammar in right linear form. So those productions are copied as such. Now, if you have productions of the form capital A giving small p, where A is not a start symbol, what you do is you add productions of the form capital S giving P capital A, where S is the start symbol. Okay. So productions of the form S giving P capital A are added to the grammar in right linear form. Now, if you have rules of the form capital B giving capital A P, where B and A are B is not a start symbol, what you do is you add productions of the form capital A giving P capital B to the grammar in right linear form. So such productions are added to the grammar in right linear form. And again, if you have a production, say production for the start symbol, that is capital S giving capital AP, where P is string of terminals, then what you do is you add a production like capital A giving P to the uh, grammar in right linear form. So this is what you do. So now let us look at an example. So in this particular grammar, capital S is the start symbol, and it is also appearing in a production uh, on the right hand side. So what you do is you add a new start symbol. So let it be S0, and you add a production like S0 giving capital S. Now S0 is the new start symbol, and naturally S0 is not appearing on right hand side of any production. So now we will use this augmented grammar, and we will convert it to right linear form. Now, so now let us convert the given grammar to right linear form. So now what you do is we will look at each production one by one. Okay. So we will look at the production A giving small a. So what we are going to do is we will add a production like start symbol giving small a capital A to the grammar in right linear form. So now we let us look at the next production. So here you have a production like capital A giving capital A small a. So corresponding to it, what you do is you add a production like capital A giving small a capital A. Now you look at the production corresponding to S giving capital S B. So corresponding to that, what you do is you add a production like S giving B capital S. So now these productions we have looked at. Now when you look at the production capital S giving capital A small b, what you do is you add the production A giving B capital S. So now you add a production like A giving B capital S. And now when you have a production like say start symbol giving you say AP, what you do is you add a production like A giving P. So here P is uh, epsilon. So corresponding to it, you will add a production like S giving epsilon. Okay. So now we have generated an equivalent grammar for the left linear grammar. We have created a equivalent right linear grammar. Now, next, what we are going to do is we look at how we can convert a regular grammar to an epsilon NFA. So that you should be clear of what we are going to convert is we are going to convert regular grammar to epsilon NFA. It is not an NFA, it is not a DFA. We are converting it to an epsilon NFA. So how do we do that? So we have three rules for that. So what you do is if you have a production like A giving epsilon, what you do is you add a transition A on epsilon, you have a transition to final state F, and F is the only final state. So since we are constructing an epsilon NFA, we can construct it with a single final state. Now, next, if you have a production of the form capital A giving small a, you add a transition A on capital A on small a, you have a transition to the only final state, which is F. And for a production like capital A giving small a capital B, what you have is you will have a transition capital A on small a, you will have a transition to capital B. So now let us see with an example. Say you are given a set of productions, and now we will construct an epsilon NFA corresponding to it. So if you have a production, say let us look at the first production. So if you have a production like capital S giving small a capital S, what you do is you will have a state for capital S, and the transition on A, you have a transition to S. So what you do is from capital S, you add a transition back to S on A. Okay. Now the next production is capital S giving small b capital A. So from S, you will have a transition on B to capital A. So next you have transitions for the non-terminal capital A. Capital A giving small c capital A. So what you have is from capital A, you have a transition on C back to capital A. And also you have a production like A giving epsilon. So if you have a production like A giving epsilon, what you do is you add an epsilon transition from the particular state to the final state. So from capital A, now you have an epsilon transition to capital F. Okay. So now you have an equivalent epsilon NFA corresponding to the regular grammar given to you. So you have to be careful that what we are constructing is an epsilon NFA. So the reason why we get an epsilon NFA is there is a chance that multiple transitions might be introduced. The transitions need not be unique. So naturally, what you might be constructing is an NFA. Also, there is possibility of introduction of epsilon transitions. Say for if you have a transition like A giving epsilon, so you will end up with an epsilon transition. So that is how we convert a regular grammar to epsilon NFA. So now let us look at how we can convert a finite state automata to regular grammar. So if you have an epsilon NFA or if you have an NFA, we know that it can be converted to DFA. So we will look at how we can construct a regular grammar when we are provided with a DFA. So basically we have three rules. That is, if you have a transition like Qi on A, you have a transition to Qj. What you do is you add a production like Qi giving small a Qj. And if Qj turns out to be a final state, you also add transition of the form Qi giving A. That is, you are reaching a final state, and now that string is an accepted string, so you need not have any non-terminals left there, so as to get rid of the only non-terminal that appears in each and every sentential form. You will also add productions of the form Qi giving A whenever Qj is a final state. And also, if your initial state is a final state, you will add transition of the form Qi giving epsilon, where I is 0 here. So, or you can say, if Q0 is your initial state, you will add productions like Q0 giving epsilon. Okay, so that is what you do in order to convert a DFA to regular grammar. So let us look at an example here. So you have a DFA with two states Q0 and Q1. So now, first we will consider for Q0. So for each state you will have non-terminals. So corresponding to Q0 we have capital Q0. For Q1 you have capital Q1. Okay. Now, so corresponding to Q0, you see that it has got two transitions. So that is, and also one transition is leading to a final state. So corresponding to these two transitions, that is, you have a transition from Q0 on B to Q0. So you have a transition like Q0 giving B Q0. Now you have a transition from Q0 on A to Q1. So you add a transition like Q0 giving small a Q1. Also, since this transition is to a final state, what you do is you also add a transition like Q0 giving small a. Now let us look at the final state Q1. So Q1 also has got two transition, and one transition is back to itself, and Q1 is a final state. So you will have three transition in total. So Q1 on A, you have a transition back to Q1. So you add a production like Q1 giving small a Q1. Next, from Q1, you have a transition to Q0 on B. So corresponding to it, you add a transition like Q1 giving small b Q0. Also, since this transition is that is from Q1 on A, you have a transition to Q1, and Q1 itself is a final state. So corresponding to it, you will add a transition like Q1 giving small a. Okay, so that is how you convert a DFA to regular grammar, or how that is how you identify an equivalent regular grammar for a given DFA. So now we will look at a particular type of representation possible for regular grammar. So according to the definition for regular grammar, you have two types of, you might have two formats for the productions in regular grammar. So if it is a right linear grammar, you will have productions of the form capital A giving uh, small x capital B, where x is string of terminals. It can also be epsilon. Again, for capital, again the next format is you have productions of the form capital A giving x. So now we are going to talk about a format where we are going to limit x uh, to have at most length 1. So now if you have a production like capital A giving small a, small b, small c, capital B, what you can do is you can limit the number of terminals to be at most 1 in a given production by introducing some new non-terminals. So we are introducing new non-terminals. So here, for this purpose, we will be introducing two new non-terminals, that is A1 and A2. First production will be A giving small a A1, and now this A1 will give you B A2, and this A2 will give you C capital B. Okay. So now by following this method, what we can do is we can limit the number of terminals that will appear in a right linear grammar to be at most one. So next what we are going to discuss is we are going to discuss equivalence of finite state automata and regular grammar. So this proof will have two parts. The first one is, in the first case, we will see that for a given right linear grammar, there is always an epsilon NFA which is equivalent to it. So what you see is for every right linear grammar, we will show that we will be able to construct an epsilon NFA. So since now NFA, epsilon NFA, DFA all are equivalent, the second part what we show is that for a given DFA, there is always a right linear grammar equivalent to it. So first we will go to the first part of this proof. So the first part is for a given right linear grammar. So for a given right linear grammar, there is always an epsilon NFA. So again, we are going to prove this using mathematical induction. So what we need to prove here is if in the right linear grammar from S, starting with the start symbol, if we are able to derive a sentential form like Wx, then in the corresponding epsilon NFA, starting from capital S, which is the initial state, on reading W, we will reach a state capital X. Okay, so we have already discussed the rules of how we do that construction. So according to this, according to those rules, when W's length is 0 or 1, it is true. So according to the rules itself, it is very clear that when W is of length 0 or when W is of length 1, it is true. So whenever you have epsilon being accepted, there will be a transition which will take you to final state. If it is a single non-terminal that is being derived also, then from A on reading small a, you will have a transition to final state. Another possibility is you have a production of the form capital A giving small a capital B. So corresponding to it, you will have a transition like from state capital A on small a, you will have a transition to capital B. So whenever the string length is 0 or 1, it is true. So that forms the basis for our inductive proof. So now we assume that it is true up to n minus 1 application of derivation. So that means from S, by applying n minus 1 steps of derivation, if we get a sentential form Wx, where W is string of terminals and capital X is a non-terminal, then we assume that in the case of our epsilon NFA, starting with the initial state capital S. So now this capital S is the initial state of the epsilon NFA. So from the initial state on reading W, we reach the state capital X. So that is our assumption. So now based on this assumption, we need to show that it is true for application of n derivation steps. So now let n application of derivation steps starting with the start symbol gives us a sentential form of the form Wxz. Okay. So now when you applied n minus 1 times, you got a sentential form Wx. Now when you apply one more derivation, you are getting W small x z. Okay. So now what does that tell you? So if you want from this sentential form, So from this sentential form, if you are getting the next sentential form as W small x z, then that tells us that there is a production of the form capital X giving small x z. Okay, so there is a production of the form, there is a production of the form capital X, this capital X giving small x z. So that is how you generate this particular sentential form. So then what should be there in the epsilon NFA that we have constructed? So corresponding to this production, that is corresponding to this production, in the epsilon NFA, there will be a transition like this. That is from capital X reading small x, you have a transition to capital Z. Okay. So now, so what does that tell us? So since when we read the string W starting with the initial state S, we had reached the state X. And now what this is telling us is there is a transition from the state capital X on small x to capital Z. So that tells us that if we read the string Wx starting from the starting state capital S, then we are going to reach Z, because after reading W, we will be in state capital X, and from capital X, reading the small x, we will reach the state capital Z. Okay, so that is so now what we have achieved so far is we have been able to show that if S capital S derives Wx, then in our epsilon NFA, starting with the starting state capital S, reading W, we will reach capital X. So that is true in all the cases. Now to complete the proof, what we need to now now convince ourselves is that, so whenever S derives a string of terminals W, where W is string of terminals, the epsilon NFA will definitely have a path that will terminate in the final state. So that is very evident, because here you are during the last derivation step, you will be deriving epsilon, or you might be deriving a non-terminal. So in the corresponding epsilon NFA also, what is happening is you will end up in a final state. So, so we can say that precisely when the precisely when our right linear grammar derives the string of terminals, we will also be reaching the only final state in the epsilon NFA. So now we can say that a right linear grammar and an epsilon NFA that we generate using the rules stated here are equivalent. So now what we have shown so far is, if you have a regular grammar which is in right linear form, we can always construct an epsilon NFA which is equivalent to it. That is, this epsilon NFA will accept precisely the same strings that is accepted by the or generated by the right linear grammar. So their language are same. So now there could be a case such that there might be epsilon NFAs for which a right linear grammar might not exist. So we must show that such a case is not possible. So for that purpose, now what we are going to do is we will show that for every DFA, we can construct a right linear grammar for it. So now in the second part for this proof, we are going to show that for a DFA, there is always a right linear grammar equivalent to it. So as part of this proof, what we need to show is that in the DFA, starting with the initial state Q0, when we read any string W, if we reach the state Qj, then correspondingly in the right linear grammar, starting with the start symbol capital Q0, there is always a derivation which will give us the sentential form WQJ. So for this, again we will be using mathematical induction to prove this. So our basis case is when the string W is of length 1. So it is very evident from the rules of construction. So basis is true because for uh, for any transition Q0 on A, if you have a transition to state Qi, then correspondingly in the right linear grammar there will be a production Q0 giving A Q1. So when you have a transition of the form Q0 on A giving Qi, in the right linear grammar we will have the corresponding production Q0 giving A Qi. So that tells us that from Q0 we can derive the sentential form A Qi. So for when you have a string of length 1, it is true. So now we are going to assume that it is true for strings up to length n minus 1. So whenever we have a string of length n minus 1 or less than n minus 1, it is true. And now what we are going to show is that it is true for strings of length n as well. So according to our assumption, we know that from Q0, the initial state, reading the string W, we reach Qi, and correspondingly using our right linear grammar, starting with the start symbol capital Q0, using n minus 1 derivation steps, we can reach a sentential form WQi. So that is as per our assumption. Now we are going to show that it is true for lengths for strings of length n as well. So now let us consider the string WA. So from the initial state Q0 reading WA, we reach state QJ. So that implies that there is a transition from state Qi on A to Qj, because when we read the string W starting from Q0, we reached Qi. So there we were dealing with a string of length n minus 1. So when we read the string W, which is of length n minus 1, we were reaching Qi, and now reading A, we are reaching the state Qj. So since we have a transition, that is Qi on A, you have a transition to Qj, then accordingly in the right linear grammar we will also be having a production of the form capital Qi giving a Qj. So that is as per our construction rules. So now if you look at the derivation that that we saw just before, that is when we had done n minus 1 steps of derivation, starting from the start symbol Q0, doing n minus 1 steps of derivation, we got the sentential form WQi. So now, according to the rules of construction in our grammar, there should be a rule like Qi, capital Qi giving a Qj. So if we apply this production here, what we get is we get a sentential form WAQJ. So now what we have shown is that it is also true for strings of length n. So here, starting with the initial state Q0 reading WA, when we reach the state Qj, accordingly we have a derivation where we start with the start symbol Q0 and we derive the sentential form WAQJ. So now we have shown that it is also true for string of length n. So our proof is almost done. So now what we need to convince ourselves is regarding the acceptability of the strings. So to complete this proof, we need to observe that starting from the initial state Q0W, if we reach a final state F, whenever we are reaching any final state, and FB, capital FB, just one of those final states, then accordingly in the grammar, what we will have is starting with the start symbol, which is capital Q0, we will be able to derive the string W. This is true because in the last step uh, of the derivation, since there is a transition to final state, we will be able to derive a single terminal, and the only non-terminal will be removed from the sentential form. So we will be able to generate precisely W following the transitions in the case of DFA. And so in the corresponding right linear grammar, we will have a derivation where we will start with the start symbol, and we will be able to derive W exactly. So that completes our proof of equivalence of finite state automata and regular grammar.